And welcome to day 2 of Calculus 2. So we're going to start today by talking about something called fluid force. Now, if you've ever been swimming in a pool, let's say a really deep swimming pool, and you're, let's say at the bottom, you might be of a 10, 12-foot pool, and you're at the bottom of the pool, why does it feel like there's a bazillion pounds of water on your head? Make sure you're muted, please.
Sorry about that, Professor.
Yeah. Now, why does it feel like there's a bazillion pounds of water on your head when you're at the bottom of that, deep pool? Does anybody know? Why does it feel like that?
Because there is.
Because there is. Good. Because there is. So the question is,
of the water,
when you're at the bottom of the pool or you're swimming in the ocean and you're really deep, how do you calculate that force that you're feeling on your head? Well, it's actually a fairly simple thing. It's quite literally the weight of the water. But what about a swimming pool? What about the sides of the pool? How are they affected by the water? And that's actually what we really want to look at, because figuring out the force on the bottom of the pool is a very simple notion. It's just simply the weight of the water. But on the sides of the pool, it's not exactly the same thing. So all liquids have a certain density. And remember, we talked about density last day, but in this case, density will be, in this case, involving weight rather than mass. Because if I'm talking about water or any other liquid, I'm interested in how much weight there is. So in this case here, the density we're going to use will be weight per volume. So it might be things like pounds per cubic foot or newtons per cubic meter or something like that. It would be the weight unit, either it's going to be pounds or newtons. And if it's pounds, it'll be cubic inches, cubic feet, whatever. Or it could be gallons. Okay, that's also a volume measurement, but it's going to be weight per volume. That's the density we're using here. Now, if you remember yesterday, I said technically there's 6 forms of density: mass or weight in the numerator and length, area, or volume in the denominator. It's a context thing. Depends on what we're talking about. Now, when you get your tires filled up, right, and you're going to go inflate your tires properly, and you might be going to the gas station, you might be going to the tire place, and they'll tell you, okay, what level do you want them set at? And they might say 35 or 38, and they'll say PSI. What is that? What is PSI?
Square inch.
But what per square inch?
Pounds per square inch.
Pounds per square inch. No, that's not density.
That's pressure.
That's pressure. Good. And it's similar, but it's not the same thing. Pressure, we generally think of as weight per area. So here's a way of thinking about it. Okay, I'm at the bottom of the pool. The area of the top of my head is where I'm feeling the water. I'm not feeling it elsewhere. I'm feeling it right on the top of my head. So what I'm feeling is the pressure of the water. Now, how does the weight come into? Well, if pressure is weight per area, I would need one more unit of measurement in order to figure out how to get density. So there's one other thing that we have, and that's depth. How deep are you? And we know that the deeper you go, the more you feel the water pressure, the more you feel that weight on your head. So depth is a length unit, isn't it? So first of all, let's figure out, how do we relate these 3 things here? I have density, I have pressure, I have depth. How do I get from one to the other? Well, if you think about it, if I multiply this by a length unit, volume is a length unit cubed, I would get area. So clearly, if I multiply depth times density, I will get pressure. Okay, that's where it comes from. Or if you said pressure divided by depth, you'd get density. But here's kind of a relationship here. Okay, so then how do I get the weight of the water on my head? I would multiply by the area. That's why the pounds per square inch matters. So another way of thinking about it, if you have a really large area and you have a certain amount of weight that's distributed over that large area, like water, the pressure isn't very much because the weight of the water is very spread out. So you have a large denominator. But if I take the same amount of water and I reduce the area to a very small amount, The weight of the water didn't change, but the pressure did because the area is much smaller. Smaller denominator, more pressure. So if I wanted to figure out the force on the bottom of the pool, that's a really simple thing. I just figure out the area. Okay, that's a very simple thing. So I've got the depth, the density gives me the pressure, and I multiply that by the area, that gives me the weight. So finally, if I multiply this, I'll put times the weight. Okay, I'm sorry, not times the weight, I'm sorry. Times the area, I will get the weight or the force. So think about it in terms of units. Length, force per volume times area. Area times the length will cancel with the volume, and that's where I'm going to get the force. In this case, if it's this way, I'm thinking of the weight of the water. But what if it's against the wall? Now, here's an interesting concept. All right, we're going to fill up your house today with water. We're just going to fill it up for fun. We're going to seal your house up and fill it up with water. Okay, so as long as the floor, there's no leaks, you're okay. But what about the walls? How much force is there against the wall? Now, here's an interesting question. Okay, let's suppose I'm talking about water is against this wall. As I move across the room all the way to the other side of the room, is the water on the other side of the room affecting the water or the force against this wall? Or is it only the water that's literally against the wall? Well, it turns out it's only the water that's against the wall. So all I really need is the area of the wall, how far back it goes. So you have a very large swimming pool. It's only the water against the wall that's affecting the wall. So that's where I have to make sure it's strong enough and isn't going to leak and all that. And I can actually calculate that, again, using this concept. So finding the weight on the bottom of the pool does not involve calculus, not even close. That's a very simple notion. So what I want to do is I want to imagine that I have some...
Professor?
Yes.
When you wrote depth times density times area equals force, is the force is the same as pressure? Isn't?
No, pressure is force per area. That's why we multiplied by area. See, remember before it was equal to pressure? So then when I multiply by area, that cancels the area in the denominator of pressure, and that's where I get the weight or the force. Okay.
Oh, okay.
Now, force is general, weight is a specific type of force. See, if I'm pushing on something, I'm applying force, but you're not saying how much I weigh, it's how much force. But if I'm just standing here, the force against the floor is my weight. Does that make sense?
Yes.
But we're now talking about, think sideways for a moment here. So it's not the weight, but it's still force. So imagine, I'm going to do this differently. I have, okay, here's water. Here's I'm underwater, and I want to know how much force is there against the side. Ooh, well, the depth matters because the deeper I go, the more pressure there will be and force against the side. So what we're going to do is we're going to break this up. So if this depth, let's call that yi. Now, depth is one of these odd things. When you go swimming in the water and I say, oh, how deep did you go today? Well, let's see. If I call the surface of the water 0 and I'm 10 feet underwater, do any of you say, oh, I was negative 10 feet today? By the way, I'm a certified scuba diver. I haven't dove in many years, but I used to dive. And if I went 100 feet deep, do I say I'm at negative 100? Or do I say I'm 100 feet deep? Nobody uses a negative number when they describe depth. Depth is one of the rare times that we reverse the number line. In other words, if 0 is at the top, we measure depth positively as I go down. If you're 10 feet deep, you don't say you're at negative 10. You say I'm 10 feet deep. We generally don't think of the bottom as 0. So if you were out in the ocean and I said, oh, how deep did you go today? Well, I was 300 feet from the bottom of the ocean floor. Well, that's not very helpful. How far were you from the top of the water? Oh, I was floating around on the top. You would always measure depth from the top down in a positive manner. So if this is my depth, okay, let's suppose we have water or any other thing, then the density is always given. Density in this case is not a function, it's a constant. whenever you have a liquid, the density is, we always consider it to be constant. Water has its density, oil has a density, everything has its own density. I'm not worried about the numbers. Heck, I'll just make up the numbers half the time anyway. So I need the area of this piece, I need the depth, and I need the density. Remember, that's what we said the force was. So the force on this little slice here, let's call that the ith slice. The force on my ith slice, we said was the depth times the density times the area, which in this case would be, we'll just call that, you know, whatever that length is. So we'll call that piece just, how about area? Or actually, let me call it AI. I didn't give you a function. That would be the force on that slice. Now, what I'm going to do is say the total force will be add all of these up, and then that translates directly into an integral, as we will see. So setting up the integral is actually quite simple. What's different for us is we're not used to measuring force against a wall, but this is exactly how I do it. So imagine at the top of the wall, is the wall feeling a whole lot from the water at the top? No, it's feeling a lot from the water at the bottom. In other words, the bottom better be more stable. So if you have a swimming pool, if you ever look at a pool when it's empty and see where the cracks are, the cracks generally aren't at the top, they're going to be at the bottom because that's where most of the force is. So we're going to do a couple of really simple examples of this. All right.
So in that drawing that you had, would the integral that you made be in respect to y instead of x?
Oh, always, because yeah, you're only measuring vertically. So that would mean when I'm describing my area, I have to convert it. That's, by the way, hold on to that thought because that's exactly what we're going to do. So here's what I've got. I've got a triangular water trough. I'll do my best here to draw. Yeah, I've got a triangular water trough, okay? Now the question is, does it matter how far back it goes if I want to find the force against this side? Does it matter how far away it goes? Turns out it doesn't. That's extraneous information. If I wanted the total force vertically, yes, then how far it goes back would matter. I want to know the force against this side here. So here's what we're going to say. We're going to say that this thing here, from here to here, it's 8 feet. And across, it's going to be, let's say, 8 feet. Let's keep it really simple. And the density of the liquid involved, I'll make it really simple. The density of the liquid, let's say, is 60 pounds per cubic foot. I'm just making up a number. It doesn't matter what the number is. All right. Water is pretty close to 62.4, somewhere between 62.4 and 62.5. That's one of those universal constants that you would use in physics or chemistry. I don't need you to know that. I'm just saying, I have a liquid. This is its density. I'd like to know how much force is there on this wall if this is completely full. Well, I have a thing. This is how math usually works. When you get that job as your engineer, no one's going to hand you a sheet of paper with a bunch of equations and say, solve these. And then when you're done, you'll get your paycheck. No, they're going to give you a situation. And I have to somehow figure out, how do I do the math? You see, I'm going to have to integrate. I'm going to have a function. I've just given you a geometric shape. Where's the function? Where's the integral coming from? Well, first thing I want to do, let me draw a picture, because I only need a two-dimensional picture. So I don't need this. I just need this. So I'm going to place my X and Y axes here. And the reason I'm going to do that, it's going to make it simpler to describe this thing. So I said that this was 8 feet across and 8 feet deep. So if I center my Y axis right in the middle, that would make that point 4, 8. And that, of course, would be 0, 0. I need to figure out how to describe that area piece. So I need the equation of the line passing through these 2 points. Well, that's pretty simple, isn't it? Isn't this going to have a slope of 2? So isn't this going to be y equal 2x? The problem is, what do I need?
So it's the absolute value of y equals 2x?
No, because I'm above the x-axis here. So y is 2. This guy, I'm talking about this guy right here. It's going to be the same on the other side, but I need x equals y, don't I? Because I'm going sideways. So if y equals 2x, what does x equal?
1 half y.
Yeah, and does everyone understand? I need to use this guy because this is going to be a delta y, not a delta x. I can't force this to be a delta x. It's a horizontal slice. Okay, but because of this triangle was 8 deep and 8 across, basically this is isosceles. It's the same on both sides. Okay, so if that distance is x, then what's the total distance going to be?
2x.
2x. Beautiful. So my ith area, I will call it, is going to be 2x times the thickness, which is delta y. And remember in Calc 1, it's this guy that determines which variable you're going to use. So that means I need everything in terms of y. Well, that's easy enough, right? If y equals 2x, then this is just going to be yi delta y. Oh, piece of cake. Now, what will the range of values of y go from? From what to what?
From
0 to 8.
So, by the way, that is important because ultimately that's going to probably be my limits of integration. Now, I've got that. So I figured out the area of the slice. Remember, I need the depth. I need the density. Density is right here. So the only thing left is the depth. So do I say when I'm 1 foot above the x-axis, am I 1 foot deep? If I'm 1 foot high, am I 1 foot deep?
No, you're 7 foot deep.
No, you're 7.
If I'm 7
7
feet
feet
high, so how do I do this?
Just flip where you put the values on the integral.
There's an easier way because I need my depth. When I'm at the top, what's my depth?
0.
0.
So when I'm at 8, my depth is 0. And when I'm at 0, my depth is 8. Is there an easy way to do that? Yeah. What's my depth going to be?
Can you just put your x-axes at the top?
Well,
So 0, 0 is at the top?
I can do that, but because this is a triangle that's coming down like that, from describing the graph, it's a lot easier for me to put this at the origin. Could I have put the x-axis at the top? Absolutely. In fact, that's the only other place I could have put the x-axis. But then you realize describing the lines would have been far more complicated. So there's a simpler way of doing that. If I call my depth 8 minus y, then when I am at this point here, I have depth 0. When y is 8, I have depth 0. And when y is 0, I have depth 8. Does that make sense? So someone said, flip it. That's kind of what I did there. There is no one size fits all. I'm going to do a second example where we're going to look at it a little differently. But because of the nature of my shape, the easiest way to do the algebra and the geometry of this shape is to put this guy at the origin, right? Then everything's easier. Depth is a little trickier. So now I can say the ith force. That means the force on that slice right there is going to be this times this times this. So I'll say 60 times 8 minus yi times yi times delta yi. And so if I multiply that out, by the way, whether you choose to multiply the 60 in or not, it's really not that important. I'll multiply it in. So I have 480 yi minus 60 yi squared delta yi. Now, I'm going to do the formal. You don't need to write this down, but I want you to remember where it came from. In Calc 1, what we said was, okay, this is an arbitrary slice. So my overall force, I would add all of these up, and I'd say the overall force can be estimated by, it's not equal to, I'd estimate it by adding up all the little rectangles of this. I don't leave myself much room. Delta y, boom. But then where does the force come equal? That's what the Riemann sum is. That's where we did the limit as the norm of the partition approached 0. The norm of the partition means the largest such delta y of the same thing. And then we wrote the definite integral. So if you remember the order of things. But after a while, when you started doing areas and volumes, you realized once you made this statement here, yes, all of this was correct, all of this was necessary, but didn't you at some point write a definite integral that looked like this, 480y minus 60y squared dy, y we said is going from 0 to 8, meaning we kind of go we jump right down to here. That's what we did in Calc 1. Once we understood the process, we could skip all of this. And I still want to do that. Understanding this is the validity of the integral. It came from all of this. But once I came up with the arbitrary slice, that's what my integral is. So why not just go from here to here? It's just more convenient because we already understand the route. So whatever I get here will be the answer to the problem. So I am going to go ahead and erase this. I need the space. And that integral, by the way, is pretty darn simple. So that integral, let's go ahead and integrate. That will be 240y squared minus 20y cubed from 0 to 8. So get out the calculator. You can do it in your head, great, but why take a chance? So 240 times 8 squared minus 20 times 8 cubed. And I get 5,120. 5,120 what? Okay, what was the question again? What's the force on that trough?
Newtons?
Should be pounds.
Oh, I just got two different answers. Which one?
I would say pounds because
It would be pounds.
The density is in pounds.
Now, is the answer pounds or is it pounds per?
No, it's pounds.
How do you know it is
force.
just simply pounds? Because
It's a unit of force.
It's a unit of force. Perfect answer. The only question is, okay, once I know it's a unit of force, my only two choices are going to be pounds and newtons. Not pounds per or newtons per. It's going to be one or the other. How do I know which one? That goes down to what was the density defined in. And by the way, the density was pounds per cubic foot and my shape was measured in feet. So this is going to be lbs. That actually should be a fairly simple notion. Okay, that it's pounds. What else could it be? Yet, when I ask this question on a quiz or a test, I'm going to get this the vast majority of the times, but I'm not always going to get this. I'm going to get pounds per or newtons per when we forget, no, this is just force. Now, don't confuse this with the spring problem where we had a force constant. That's totally different. And in the spring problem, we were calculating work. So that was force times something. So in this case here, my density, we integrated over the density. That's why it ends up being just pounds. And this is a fairly harmless problem. Well, it's fairly harmless because my region was really nice. I mean, I'm bounded by a couple of lines and that was nice. But let's do a little more complicated one than that. I don't want to say harder, just a little bit more complication. Now, I don't know if, and like I said, I used to dive a lot. And I used to like to go out in the bay. There's a sewage pipe that goes way, way out, like 3 miles out. And some of the best life in the ocean, all the kelp beds and things like that are kind of hanging out there. And as long as you aren't near the end of that sewage pipe, you're probably pretty good because it goes pretty far out there. But the question is, if I've got a sewage pipe, okay, this is going really long, but let's say the sewage pipe is half filled and you've closed the pipe at one end. I mean, it's not continuously open. You've closed it at one end. It's half full of whatever it is. I'd like to know what is the force on this face right here. So again, the length of the pipe is irrelevant if I'm only asking for the force here. Now, in this case, I'm going to give you a sewage pipe that's exactly half filled. By the way, I could make it any fraction of the way, but half is an interesting problem. We'll look at that. If it had been completely full, that's another thing. So now the question is, where do I want to put my axes?
I'd say at the bottom.
Now, this is a circle. And let's say, in fact, let me say, I have a circle.
You'd want to.
It's 10-foot diameter. Okay. And what else do I want to use? It's 10 foot. It's half full. It's 10-foot diameter. And let's say the density of the sludge this time, we'll say 75 pounds per cubic foot. I'll use a different number. It's definitely not water. And it's probably more dense than water. Well, it's a circle. In the last case, I had a triangle. I put the point of the triangle at the origin because it made it really easy to describe my boundaries. I have a circle. Do you think I want to put my y-axis on the side here?
No, probably just put the origin at the center.
Yeah, in that case, the most logical place would probably be to put the origin at the center, simply because it would be the easiest way to describe the equation of the circle. And then we can worry about depth and everything later. But what I really want is the easiest way to describe my boundaries. That kind of takes priority. I can put the center anywhere, but this is actually going to be the most logical. It's not the only way, but it's probably going to represent the easiest way. So I have a circle of radius, what?
5.
5. So that means it's going to be x squared plus y squared equals 5 squared. It's only filled on the bottom half, so I need to do my arbitrary slice down here. So like before, if from here to here is x, I need 2x. And like before, we measure depth this way. But remember in the last problem where I did 8 minus y because I wanted the depth to stay positive? Now this is easier. If I'm here, my depth is 0. If I'm all the way at the bottom, my depth is 5. So I'm just going to call that y. I don't need to call it negative y. I'll just call my depth y. I am y feet deep. So if I'm at the top, y is 0. So here's the one where the y's really will go in the reverse direction. And y is clearly going to go from 0 to 5. So the first thing I need to do is write x in terms of y. And again, if I'm calling this distance x, then we're going to treat x as a strictly positive quantity. So I can say that x is the positive square root of 25 minus y squared. I can say that because of how we've set it up. So now the ith area, you said before, was 2x. So just like before, be 2 of these. Now, because I'm going to have a square root in an integral, I can write it as to the 1/2 power. That would probably make sense, or you can write it as the square root. It doesn't matter. At some point, you'll probably want to change it to the half. And like we said before, y is going to be between 0 and 5.
Professor, could be a dumb question, but where did you get the area equation, the a equals 2x delta y?
Oh, okay. Well, first of all, I need to find the area of this strip. So from here to here, that's x.
Got it.
So all the way across is 2x. But I need x in this circle. X is going to be the square root. We're used to thinking y equals, but because I'm always measuring everything up and down, I need everything in terms of y to make this make a little more sense. So like before, the ith force, it's area times depth times density. So it's going to be this times the depth. Oh, sorry, I'll put the delta y at the end, actually. I got the 70, I'll put the 75. I've got the y and I got the delta y. What order you wrote them isn't really all that important. Now let's be lazy. Let's go right to the integral. Once I set up my arbitrary slice, I can go directly to the integral. Okay, so I can certainly multiply those two. So my force is going to be the integral from 0 to 5 of. So that looks like 150 y square root of 25 minus y squared dy. That's not quite as easy as the last one, is it? Do I know any way of doing this guy? Because that square root, that kind of throws a monkey wrench into this, doesn't it? I'm going to erase this for space. Do you know any Calc 1 techniques? You see, the problem is my argument. This is my argument right here.
We can use the U substitution.
Why can I use the U substitution? Because I have a y right there. Excellent choice. If this was not a y, if that was a y to a power or something else, I'd be kind of stuck. But because I have basically the chain rule factor or a multiple of it sitting right there, this one is perfect for U substitution. And that's probably why I chose this one, just to give us a little review of how to do a U substitution on a definite integral. And I mentioned before, of all of the skills you learned in Calc 1, this is A number 1. This is the single most important skill you learned in Calc 1. It's the single most important skill you're going to do in Calc 3, in differential equations, in upper divisions. It's the ability to substitute in a definite integral because I have the limits to worry about. So we'll say, let's let u equal 25 minus y squared. Then what's my du? That'd be negative 2y dy. And I certainly have a multiple of that here. But lastly, my limits, my y limits, I'll write it here. My y limits are going from 0 to 5. What will my u limits go from? Well, when y is 0, what's u?
25.
25. And when y is 5, what's u?
0.
0. Oh, that doesn't look that bad. Now, before we can do the substitution, and by the way, I'm going to review this, but this is, I find that having been a calculus instructor ever since Professor Newton let me start teaching his stuff, a few hundred years ago, I find that people come up with their own versions of the truth. That's a nice way of me saying. In other words, they kind of make it up as they go, and they're almost certain somebody showed them something that actually isn't true ever. No, a U substitution is absolute black and white. There are no gray areas. You can only do a U substitution if the chain rule factor is part of the integrand. Exactly the chain rule factor. And that refers to exponents as well as coefficients. That means I need exactly a negative 2y. Oh, well, that's easy enough. I just factor some of it out. So I'm going to rewrite this as, first I'm going to write that as 25 minus y squared to the 1/2 times negative 2y dy, which leaves what in front then?
75.
Negative 75. Have I actually done any math yet? No, I just rewrote it. But I rewrote it in exactly the form that I want to substitute. That's always a good idea. So now this is negative 75 u to the 1/2 du. Oh my gosh, that's beautiful. But not from 0 to 5. That would give me a very different answer. In fact, it wouldn't even be a similar answer from 25 to 0. And all of a sudden, that doesn't look so scary. So I'm going to move it up to the top. The antiderivative of u to the 1/2 is u to the
Negative 1/2. Oh, 3/2.
Wrong way. 3/2. 3/2 times 2/3. But I already had a negative 75. What's 2/3 of negative 75? It's a nice number.
Negative 50.
25.
Negative 50. Now, by the way, this is where I always recommend people stop. Don't take another step. Check. How do you check? Take the derivative of this. 3/2 times negative 50 would be negative 75 u to the 1/2. Okay, good. Always check your antiderivative right when you do it because, for example, somebody hollered out the wrong exponent. Common mistake. Somebody hollered out the wrong coefficient. Common mistake. But the check is so easy. Take the derivative of that and do I get back this? Okay, I did. Now I know this is correct from 25 to 0. And you're saying, but my limits are backwards. Yeah, but I also have a negative here. That's a good thing. Because when I plug in the 0, I get 0 minus negative 50. So that's 50 times 25 to the 3/2. 25 to the 3/2. That's square root cubed. That's a nice number. So 25 to the 3/2 is 125. And I'm multiplying that by 50. And that gives me 6,250 what?
Pounds.
Pounds, just like last problem, because I gave you density in pounds. And it turns out the reason the answer came out so nice really was because I chose a density that was really nice. Now, in real life, nobody has to memorize densities. In fact, if you were in a physics class, you would probably have a sheet that gives you many, many, many different liquid type substances, and it would give you all their densities so that when you're doing the problem, you just, crank it out. It doesn't matter what the density is. The fact that I gave you a density of 75, did that change any of your calculus? No, it only changed what number you wrote in the problem. I could have said the density was some icky, hideous decimal, and then you would have just carried that through to the end of the problem. I chose a nice round number to make the numbers work a little nicer. Now, this is pretty much every example you really need to see to understand fluid force. So in fluid force, If it's vertical, you're literally calculating the weight of the water. That's boring. That's not calculus. That would be like saying, what's the volume of your rectangular living room? I just multiply 3 numbers together. Yeah, in other words, that's how simple it is finding the weight on the bottom. Okay, that's kind of like just saying measure a scale. But the weight against the side, we actually have to slice it and we have to integrate. And the difficulty of the problem is entirely based on the complexity of the region. My first example, my region was triangular. I had to do a little work. In this example, the region was circular. What if my region had been rectangular? Do you think that would have been a very difficult integration?
Yeah. I mean, you can't do it because it's not a function.
Well, no, it would mean that number there is a constant as opposed to something times a variable. In other words, it would have been an easier integration.
Oh, okay.
It would have been an easier because instead of a function here, I would have had a constant there. I still have the rest of the problem. That's okay. So again, based on the complexity of the region would determine the difficulty of the problem. What's the most important thing that we did in this entire problem? Coming up with that integral. That's the most important part of the problem. If I can get the integral, I can go. Now remember, it is possible that the region is so complicated that you can't integrate that, but you could state it. So in the future, you'd say, well, what do I do if I can't integrate it? You're going to not only learn more techniques, but you're also going to learn ways of doing very powerful estimations later on in this course. So there's really going to be no problem that will escape you. It's kind of cool. All right, now we're going to do a very different application. And this one is, there are units, but the units now are not really that big a deal. It's not physics type units. Our unit might be temperature, or my unit might end up being, volume, or, something really, really simple. We're going to do what's called, I'm going to do the generic population growth problem. Now, when I say generic, population doesn't necessarily refer to people. It's something is growing. The population could be, I have a crystal and the crystal itself is growing. It might be I have the bacteria in the petri dish and they're growing at a certain rate. It might be a world population. It might, but it also could be population decay. That means I'm actually losing stuff. So like radioactive decay, things like that. It's all generically called population growth. And there's one equation that governs this that is universal and we've always accepted. So if I say,
I have a question about the TAN book. My question is this the same chapter as the predator-prey models, or is that a different chapter?
Oh, I don't have it in front of me. Why don't you do me a favor? Send me an email.
All right.
Just send me an email, and when I see it, I'll look it up. I don't have it in front of me and memorized. So, fluid force in your textbook should be located relatively close to wherever the work was. And most of the time, I have a lot of calculus books, and most of them, they're consecutive sections, just like we did, because it's the same type of mathematics, different application, but the same level. So if I said, let y of t be the population after time t. Now, what are we measuring t in? Well, it depends. I could be measuring t in years. If I have a highly unstable radioactive substance in a chemistry lab, I might be measuring t in nanoseconds. That's billionths of a second. There's no rule for what t is measured in. So whatever your problem is, you'd be told we're going to measure t in nanoseconds, in seconds, in minutes, in hours, in days, in years, in centuries, whatever it is. So if we do a human population, it's probably going to be measured in years. Okay. So if y of t is the population after time t, then dy dt, which is the instantaneous rate of change of my population, is equal to a constant times my population. This is the universal equation that governs all population growth or decay. Think of this, let's overly simplify this, and let's think of this like money for a second. So if I said, all right, you're going to put some money in the bank, and you're going to, let's say you're getting 5% interest. Oh, okay. Well, how much money will you have in a year? I don't know. Depends on what? How much you put in. So in other words, this is like the interest rate. This is how much you're putting in. The rate of change is a constant multiple of how much you have. So if you said a population in a certain region of the country is growing, 3% per year, 3% per year doesn't mean a certain number of people per year. It means 3% of whatever the population is per year. Right? So if you put money in the bank, the more money you put in, the more money you're going to get out. So you don't say, oh, my bank promised me I'm going to earn $100 a week in interest. No, they can promise you a percentage of what you put in interest. So population growth or decay, the rate of change of the population, this would be then, if I'm thinking people, this would be number of people per year, is a constant multiple of the number of people. Now, we notice this not because somebody came up with this, but we notice this through observation, and all populations grow and decay over a finite period of time. And this is very important to realize. You guys all remember this, high school history books or social studies and things like that. It'll say, things like, in 1976, the Earth's population was 4 billion. That's true for like 1 second. In 1976, the Earth's population was 4 billion. Does that mean it stayed 4 billion the entire year? No, it changed several hundred million over the course of the year. So in other words, we say there was one moment in time that we hit 4 billion and we passed on. Populations grow and decay over finite periods of time at relatively fixed rates. Investments grow or decay for finite periods of time at fixed rates. You can't say something's going to grow at this rate forever. That's not how it works. Limited resources and space. But we say over a finite period of time. Now, there are certain things that do decay. Now, radioactive decay and things like that, that actually does stay the same. I want to solve this differential equation. That's what this is. Any equation involving a derivative is called a differential equation. This is the most basic one that exists and is considered one of the more important ones. So for me to solve this, first thing I'm going to do is multiply both sides by 1 over y. And I will have 1 over y dy dt equals k. Now, the independent variable in this problem is t. Y is the dependent variable. I can't integrate with respect to y. I've got to integrate with respect to t in this case. So when I integrate both sides with respect to t, this is very much like what the U substitution looks like. I mean, it's really the same sort of mathematics. dy dt integrated with respect to t is the same as integrating with respect to y. And again, in the U substitution, you integrated du dx with respect to x, and that gave you the integral of du. And I will go over that again later. And there's also some published notes. So when I'm integrating this, I don't actually see a t in the equation. I only see a y. And on the other side, I have k dt. Now, 1 over y dy, the antiderivative is natural log, as we know. On the right side, it would be, that's a constant, so kt, and then plus constant. I'm going to call it c1, because it's going to change. So we've just integrated this. Now, I'd like to write y equals. Y was a population, so y can't be a negative number. The antiderivative of this is log of absolute value, but in this case, this y is a strictly positive quantity, unless, of course, I have 0 people, in which case I'll continuously have 0 people. So when I exponentiate both sides, I will get y equals e to the kt plus c1. Rules of exponents tell me this is equal to e to the kt times e to the c1. Now, if c1 represents an arbitrary constant, and doesn't e to the c1 also represent an arbitrary constant? This c1 can be anything positive or negative. This is e to the c1. That would have to be strictly positive, wouldn't it? So why don't we, for lack of a better name, call that c2? Or even just c. I said it's going to change. So here's what I got so far. I've got y of t equals c e to the kt. That means that the population is growing exponentially. What I don't like is I have 2 constants in my answer. I really would rather not. Now, k is either going to be given, the population is growing at this rate, or k absolutely can be calculated. If I said today the population is this, tomorrow or next year or 10 years from now, the population is this, you can calculate the value of k pretty accurately. So k is either given to you or you can calculate it. What about that guy? Well, right when I started, if I said the population today is, That's called our initial population. We often refer to that with a subscript of 0. In any situation in math and science, when you use a subscript of 0, that always refers to an initial condition. So if I said y of 0, sometimes we write it like that. Y sub 0. Well, what is y of 0? That would be c e to the 0. But that's just c. Oh, so this c that we called an arbitrary constant is far from arbitrary constant, isn't it? It's the initial population. So now we have the final version of population growth. This is not something that people challenge or question. Anything that grows or decays is governed by this equation for a finite period of time. Why? Because the k can change. Populations like cities, they can slow down their growth. They can speed up their growth. Or worse, you have what's called a ghost town. In other words, it starts decaying and going the other way. I start having less people as a result. So for finite periods of time, as long as k is constant, all populations grow or decay this way. Well, what's the difference between growth and decay? If k is positive, it's growth. If k is negative, it's decay. Think of the shape of e to the positive, e to the negative. Now, with that, I can calculate, I can estimate. This is what cities do. This is, if I know a certain region or a certain area has been growing at a certain rate, let's say over the last several years, it's reasonable to assume it will continue growing at that rate for a short period of time. And so based on that, I can predict what is likely going to be the population next year or 10 years or so on. Okay. Now I can remember when my kids were in elementary school, one of the questions they would have in their studies, because they'd kind of lump math and social studies and different things. And I remember the question was, the population of China was this. I don't remember the number. It might be like 1.2 billion. And their growth rate is this. The population of India was like 1 billion or 0.9 billion or something, but it had a greater growth rate. And the question is, when will the population of India overtake the population of China? And there's kids like in 4th grade, 5th grade, and they would just sort of mess around. Okay, next year, and then they'd put the numbers in, and at some point they'd see, it switched places, because the initial population of one country was less than the other, but the growth rate was greater, which means if I'm looking at the curve, one grew faster than the other, so it had to pass it eventually. Some of you may remember doing problems like that, but this is the mathematics behind it. So with this idea, if I grow at a certain rate, I can go right to this. So if I told you something is growing or decaying at a certain rate, you can go right to this. Now, this is also the equation that governs things like half-life. You guys remember that kind of thing in your science classes, or maybe even your algebra and pre-calc. You might say, I have a radioactive substance and it has the particular half-life. If I start with this much stuff, when will I have this much stuff? And that's actually a fairly simple calculation involving exponentials and logs. I also might have a situation where I say, well, the population is doubling every certain period of time. When will the population be the following? Same thing. I do the exact same thing. So now we're going to do a very specific example. One of my favorite ones, because it's one of the most widely used applications, believe it or not, in real life. Okay, so here's the deal. First of all, there's only one assumption, that the ambient temperature is constant. Ambient, think of it as like room temperature. I'm in a constant temperature environment. That's very, very important. I'm not outside where it's getting cold and hot, and I'm in a constant temperature environment, and I have my cup of coffee. It's really, 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 really hot. So I set it on the counter, and what's going to happen immediately? Anybody? What's going to happen?
This coffee is going to get a little cold.
Okay.
It's going to lose.
Do you agree it'll start cooling down? Everybody okay with that?
If it's hotter than the room temperature.
Well, I said it's a really hot cup of coffee. Hopefully my room is as hot as the cup of coffee. Otherwise I burst into flames.
I missed that.
So let's call this time, and let's call this temp, capital T for temp. Okay. Here's my room temperature. Let's say the room temperature is this. And we often use a capital A, ambient. Okay. Now I took out my hot cup of coffee, and it's right here. And you all agree the coffee is going to start cooling down. Okay. Then at some point it's going to cross, and then it's going to keep going. Oh, we have a problem. Eventually that cup of coffee is going to freeze. and then it's going to keep getting colder, and it's going to start approaching absolute zero, in which case all molecular life stops and it starts spreading. And basically, we're going to be living on a frozen waste ball of ice because I forgot my cup of coffee, or not.
It reaches the room temperature.
Here's the question. Can the coffee reach the room temperature? Yes or no? It's an absolute.
Yes.
Yeah. If it reaches room temperature, then it keeps going forever and we are on a frozen bowl. Never leave your coffee out and take a chance. No, it can't reach room temperature. That's absolutely violates all laws of physics and nature. Room temperature is an asymptote. Now, I can get so close to room temperature that the difference is getting smaller and smaller and smaller, but the difference can't be zero. That's impossible. Because if it reached room temperature, that means it's not an asymptote. It keeps going. Oh, so it's asymptotic. Now, when you're measuring temperature, you got a thermometer. I mean, you're lucky if you can get tenths of a degree. You know, I could be within 100th of a degree of room temperature. So for all practical purposes, wouldn't we report? When you're reporting your temperature, you just had your temperature taken. You give 3 decimal places, folks? You probably give 1. It's rounded. So that's really not the issue. The issue is that it's actually doing this. So the question is, I would like to know, how long do I have to wait then until my coffee is at a temperature that I can drink it? Or how hot is it going to be in 5 minutes, in 10 minutes, in 20 minutes? Okay, that's a fair question. Again, the ambient temperature is the key. Okay, that because if it's not a constant room temperature, then there can be fluctuations. If this number can go up and down, then this isn't bounded by anything. So we're going to solve this problem, and it turns out it's very similar to the population growth. The differential equation here, capital T is temp, little t is time. The rate of change of my temperature per time, the instant rate of change, is going to be a constant multiple. Now, when is my curve the steepest? When this difference is largest. When is my curve the shallowest? When the difference is small. Okay, mute yourself, guys. So this is going to be a constant multiple of what? Of the difference between my temperature at any given time and the ambient temperature. Okay, this is an absolute law. This is one of the most important differential equations, and I'll explain why it's so important. Okay, but this is similar to the population growth problem that we just did. The difference is now it's this difference. Okay, when this difference is large, it cools down greatly. When I put the ridiculously hot cup of coffee out, it's going to cool down quickly. But when my coffee is only 1 degree above room temperature, it's not cooling down very fast. It might take an hour for it to drop a half a degree at that point. It might only took a few minutes to drop 20 or 30 degrees. But as this difference gets smaller and smaller and smaller, right, this rate of change gets smaller. So I want to solve this differential equation right here. So let's do this. And by the way, it's understood that capital T is bigger than A. Now, capital A is given. The measurement of the hot cup of coffee right when I start, we'd call that capital T sub 0. That would be easily measured, whether it's given or I just simply measure the temperature. So that's not in doubt. So for me to solve this, like we did before, we're going to write 1 over T minus A dt equals K. And now I'm going to integrate both sides with respect to time, because that's my independent variable. And like the last problem, that means that this becomes 1 over T minus A dt equals K dt, K being a constant. And like the last problem, this is going to be natural log. I don't need to do U substitution on this one. So this looks very much like my population growth. And finally, I can say capital T. By the way, it's understood this is T of T. I just don't write it every time because it takes time. When you're doing stuff in Calc 1, you have Y as a function of X. I'm pretty sure none of you ever wrote Y of X. You just wrote Y. It's implied that it was a function of X. It's implied it's a function of little t because of that statement right there. So I have T minus A equals e to the KT plus C1, which is e to the KT times e to the C1, which let's just call C2 e to the KT. So now here's what I've got. So finally, I can say that T of T equals, throw A on the other side, A plus C2 e to the KT. A is given. A is a constant. A is not something that has to be calculated. But like before, I don't like that I have two values there that I don't know. Those are not, I don't have any idea how to get those yet. Okay. Little k has to be calculated. No way around it. But C2, maybe I don't have to calculate that. Let's check this out. Now, right when I set my hot cup of coffee down, its temperature right at that moment, we call T sub 0. So the temperature at time 0, which we call T0, is equal to what? A plus C2 times e to the 0, but that's just 1. Oh, so that means that C2 is equal to what? T0 minus A. So C2 isn't an unknown. Now we are here. T of T equals, okay, A plus T0 minus A e to the KT. Known, 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 must calculate. Okay, so we're almost there. Now, I can't go any further until I actually have specific numbers. Given any situation, we can calculate how hot something will be in the future, how long it will take to reach a certain point. We can do all of that with just a very little bit of information. This formula here, this process I've just done is called Newton's Law of Cooling. And that was my Professor Newton, you know, the same guy, the apple hit him in the head. Yeah, Newton was a coffee guy. You guys didn't know that. So he figured this out. Now, part of the reason this is so important is the ability to calculate when things will reach certain temperatures or, you know, how hot they are at any given time. Now, here's the deal. When I set my hot cup of coffee down and it started cooling, that's great. I must take a temperature reading at some point in the future after I set it down, and usually try to pick an exact time, like exactly 5 minutes or exactly 10 minutes or exactly 1 hour. And then I have a second reading. If I give you a second reading, like for example, in 10 minutes, if I said T of 10 is 100 degrees, that second reading is how I calculate K. There must be a second reading. It's impossible to calculate K based only on setting the hot cup of coffee. And here's why. I'm brewing coffee in the other room. I'm brewing it really hot. And you decide to put yours in a really big bowl, and somebody else decided to put it in an insulated thermos. I don't think they're going to cool at the same rate. The cooling has nothing to do with the coffee. The cooling has everything to do with what you put it in. So if I put it in just a regular old mug, it's going to cool at a different rate than if I put it in a closed container, or I decide to pour it on a plate. I don't know why I'd do that, but so that all matters. That's why you take a second reading. So let's do a problem from beginning to end. And the nice thing is we can kind of fast forward. Okay, I'm going to leave this up here because this is the form that I actually work with. I derived that. So here's what I've got. I've got a metal plate. I put a piece of metal in the oven, got it really hot. A metal plate is heated to 300 degrees Fahrenheit. Now, if you have an oven, that's really not that, not that hot. I just left a metal tray in there, the cookie sheet. Could be whatever you want. Okay. I got this 300-degree sheet. Now, it's very cold outside. Okay, maybe I'm in the Northeast or something. And so I'm going to take it outside where it's already really cold. And the temperature's not really changing right now. Maybe it's the middle of the night. It's cold outside. So I'm going to place the sheet, place the plate in an environment outside that is, what did I choose? I said, hold on, 44 degrees. It's chilly. I mean, it never gets that cold in San Diego, as we know. All right. Now, obviously, the metal plate is going to start cooling rapidly. It's cold outside. But how rapidly is it going to cool? Well, I waited all of 6 minutes in 6 minutes, the temperature, the temperature is 108 degrees. Again, it's cold outside. And I've got this just raw metal plate. I put it outside. It cooled down really rapidly. It cooled down almost 200 degrees in 6 minutes. So does that mean in 6 more minutes, it'll cool another 200 degrees? We'd be at absolute zero within the half hour if that were true. No, pretty sure it's not going to cool quite as much in the next 6 minutes. So we have two things that we want to do. We want to figure out a general equation that governs the actual temperature at any given time. And then I want you to calculate, okay? Find the temperature in 24 minutes. Okay. How are we going to do that? Well, I have everything I need to know. I have my ambient temperature. I have my T0, and I have my one measurement in 6 minutes. So I'll be able to calculate the K. So I'm going to walk you through the process. You can actually do the entire problem usually without the use of a calculator, believe it or not. Usually, more often than not, you don't need a calculator to do these because you said, but aren't I going to get logarithms and exponentials? Yeah, but you're going to get e raised to the logarithm, which means I have some really nice stuff going on. So let's use this. A is, what did I say, 44 degrees. T0 is, where is it? 300 degrees. Okay, so my equation that I'm going to start with, my T of T is 44 plus 300 minus 44, 256 e to the KT. This is what I'm starting with. Okay, that's not going to help me until I find the value of K. So how do I do that? Because I said in 6 minutes, and by the way, you could use hours if you want as your time, but I'd be reluctant to use hours. There's nothing wrong with that. But now I'd be giving fractions or decimal values of time. Now, 6 minutes, 24 minutes. I don't really want to give a fraction of an hour. It would be much easier to just say T of 6, right? Nice whole numbers. That just makes the math much easier. You could use any unit you want, but since these are in minutes, I'd probably stick with minutes. So T of 6, which is 108, is equal to 44 plus 256 e to the 6k, because I replaced t with 6. I now can easily solve for k. Okay, so if I do negative 44 to both sides, I will have 64 equals 256 e to the 6k. Multiplying by 1 over, I believe that's exactly 4 times 64. So that gives me 1/4 equals e to the 6k. So finally, I've got 6k equals the natural log of 1/4. And therefore, k equals 1/6, natural log 1/4. Yes, that is a decimal value, but there's no reason for me to use that. Now I'm going to erase this because I need the space. And I want to remind you, one of the most basic properties of logs and exponentials, if I said e to the log of thing, that just equals thing, right? The e and the log undo each other. So since my k involves a logarithm and my k already lives in an exponent, it'd be much easier for me to just go e to the log, okay? Now, there's a secondary rule that we sometimes forget, and that is log x to the n equals n log x. In other words, that coefficient, right, comes down or can go back up. See that 1/6? I can bring that up here if I choose. I'm not going to choose to do it quite yet because there's a little bit more manipulation I want to do here. Let's take this and get ready to put it here. Right now, just the e to the kt part, I've got e to this times t. I want to simplify that to the best of my ability, but I'm going to use properties of logs in order to do that. So right now, I have a 1/6 times a T. Can I write this as E to the T over 6? Is that legal? I just put this over here. Can I do that?
Absolutely.
Yeah.
And then E to the log 1/4 raised to the T over 6. This is what I wanted. These undo each other, and this ends up just being 1/4 raised to the T over 6. Oh my gosh. This scary looking thing here reduces all the way to this simple thing right here. That's exactly what I want. So let's go now. I guess I can write it right. I'll put it under here so we don't lose where it came from. So now I know that T of T is 44 plus 256 times this, times 1/4 to the T over 6. This is the general equation that will govern this, the temperature of this metal plate. Now, before we take another step, is there a way to check? Because obviously errors can happen. Can I check at this point to know that this is correct? Yeah, actually the check is easy. If I replace T with 0, then this will be 1. And I'd have 44 plus 256, which is 300. As T gets bigger and bigger and bigger and bigger, won't that get smaller and smaller and smaller? If I take 1/4 and raise it to successively larger powers, isn't that going to essentially go away? So in other words, this quantity is approaching 0. So it's approaching 44 as T gets really big. Remember, we said asymptotically, you're approaching the ambient temperature. I'm approaching 44 as T grows. So I've just confirmed both these numbers. That makes me pretty confident that this is correct. If this wasn't correct, I couldn't get both of those. Again, as T grows, this quantity is approaching 0, and I'm approaching my ambient temperature, which we said we were asymptotic to. And if T is 0, I'm at 300. So now the last part of the question was, what is the temperature in 24 minutes? (24.6) is just 4. So 256 times 1/4 to the 4th, that's 1 over 256. That's just exactly 45 degrees. So this plate cooled down pretty quickly. How long will it take the plate to reach the ambient temperature? Well, it's asymptotic. So in other words, a month from now, I might be 44.0001 degrees, but I'm never going to be 44 degrees. Now, the best part is it doesn't matter. So I always like to do things like this. All right. If water freezes at 32 degrees, now it's not exactly 32 degrees. It's to the nearest integer, it's 32 degrees Fahrenheit. But if water freezes at 32 degrees, then of course you want to set your freezer to 32 degrees, correct?
Not correct.
I want to make ice cubes. And so I have my freezer set at exactly 32 degrees and I put my ice trays in there. And I check next month and it's partially frozen. And I check next year and it's maybe even closer to mostly frozen. How long will it take the ice to completely freeze? Forever. Infinity. So that's why you don't set your freezer at 32 degrees. You set it at 20 degrees. So it passes right through the 32 rather easily. Everybody understand that? A lot of people go, oh yeah, that makes sense. Set your freezer way below freezing, then things will reach freezing really quickly and be even colder. Now, there's a similar problem that we must face here. And this is something, okay, the coffee problem, clearly we've overcome, we're not going to end the world and all this kind of stuff with our indiscriminate, use of coffee. All right, so here's the situation. Same thing. Here's temp, and you pull the meat out of the freezer. Well, you can't eat it; it's frozen. So you pulled the meat out of the freezer. It's down here. Here's your ambient temperature. So the meat's going to, of course, get warmer.
It's going to do the same thing.
And of course, I forgot about the meat. It gets hotter and hotter, eventually bursts into flames, and eventually it's uncontrolled. It's going to go supernova, burn up all of the oxygen molecules on planet Earth, and we're going to be a desolate wasteland.
Unlike the cold, it doesn't have an absolute hotness. There's no absolute zero.
Or maybe it goes like that. What do you think? That
looks better.
Yeah, probably a little safer. So our frozen food won't turn supernova. By the way, you think I'm joking. It's actually one or the other. There is no third option. I either reach room temperature or I don't. If I reach room temperature, you can't reach room temperature and then go this. That would be a non-differentiable behavior, which is absolutely impossible. Things can't behave that way, no matter what. So therefore, it's the same rule. Now, I said this was one of the most practical and useful formulas, Newton's Law of Cooling. It's kind of funny where this came up the first time I really heard about it being used. Now, I don't want to mention any names because I don't want to get sued, but there was a certain restaurant, I think it was in the 90s mostly, that was notorious for serving their coffee at their drive-through at over 140 degrees in a styrofoam cup. And I'm sorry, but you got to be a blithering idiot to do the following. People would buy their coffee with the styrofoam cup, put it between their legs, and then drive off. But as it popped open, squish, and get severe burns. And so the particular Mick restaurant got sued over and over and over again. And the lawsuits, I don't know what it was exactly, but I know it was at least in the hundreds of millions of dollars. Nobody drinks coffee at 140 plus degrees. That's insane. Okay. So they figured out that, after you brew the coffee, if we wait a certain amount of time, then serve the coffee, it will be a little bit cooler and a little bit safer for the patrons. It's kind of an oh duh. And that happened. Now, you're saying, who would do such a dumb thing? I have a friend that I used to work with. His wife was he worked at Mesa. His wife was a PhD professor at San Diego State. She put a hot cup of coffee between her own legs and got third-degree burns and had to have skin grafts. A PhD professor did the same thing at her own home. She couldn't blame anybody but herself. So yeah, people do crazy, dangerous things with coffee. Be careful with coffee, please. But this was one of the simple uses. But there's actually another one. I have a neighbor, and this is just weird circumstance. When I first moved into this neighborhood, we had two different widowed elderly shut-ins, two different guys. They were in their 90s, quite literally. And they were elderly shut-ins who had been living alone for a really long time. And one of my neighbors would take them food and stuff on a regular basis. And two different neighbors he found dead. It was like 2 or 3 years apart. And I know what you're thinking. No, it wasn't like that. But in a constant environment temperature house, this is exactly what the coroner does to determine time of death. Because what they do is they take immediate body core temperature reading and then say, if the person was relatively close to 98 degrees at the time of right before they died, because most people, their core body temperature, give or take is around 98 degrees, then you could actually work backwards to say how long ago. Remember, Nunes Law of Cooling, we can work backwards and say how long ago was it at 98. Now, is it going to be exact science? No, because the temperature change isn't going to be huge, but they can at least get within a few hours. Now, the hiker is outside, they're jogging, they disappear. Maybe they found a mountain lion, something happened bad. They find the person, they find a person maybe on the trail, they've been dead for a little while. Why can't they determine time of death using Newton's Law of Cooling?
Because there's the temperature is not a constant.
Because when you're outside, there's no ambient temperature. Yeah. And by the way, that's a totally different situation. So in that case, they actually use molecular decay, rigor mortis, the gross stuff. There's other ways, cellular decay. It's a little more complicated. But in the situation where it's the constant temperature environment and not a tremendous amount of time has taken place. You see, the elderly shut-ins, if they're left too long, their body temperatures are going to be way too close to the ambient temperature, isn't it? And so in other words, then waiting a couple hours or waiting an hour to take a temperature, you're not going to see enough change. Now, I know that sounds terrible, but this is actually what science does. But this isn't even the most important one. Nope. The most important one comes from someplace else. I have a brother who's an insurance, he's a contractor and he does mainly insurance restoration. That's like when you have a flood or a fire, he's the one that comes in and saves the day. And he does that with big office buildings and different things. The most common accidents that occur with homes and buildings are fires and floods. Now, the most powerful entities in the country or in countries in general, are not governments, by the way. The richest and most powerful entities are insurance companies, just so you know. Insurance companies have significantly more money than countries do. If everybody in the United States died, the payoffs for life insurance wouldn't even be an issue. Things like that are beyond, life insurance can't be taxed. It's beyond government controls. So they talk about there's only a few things. You can't avoid death and taxes, right? Some people have figured out a way. No, there's one thing you can't avoid, and that's called fire insurance. If you're a homeowner, unless you own your home outright, you have to have fire insurance. You don't get a choice. You can't have a mortgage without fire insurance because the insurance companies don't want to lose their investment because they own the house until you pay it off. So when there's a fire, there are only two possible ways a fire can occur, and they both begin with A. Anybody want to guess what those are?
Accident or a user error?
Arson.
The insurance companies send in their crew of investigators every time there's a fire. It could be your house. They send in their crew of investigators to figure out which one it is. Because if it's an accident and you're insured, they're going to pay. That's what your insurance is for. But if it's arson, they're going to prosecute. You can't win this one. Their resources are too great. And so I asked how this works. Now, they're doing the same math we're doing, but it's a little more complicated. It involves stuff called partial differential equations, which is like an upper division class. But it's unbelievably cool. And the way, imagine you have, if anybody here who has an outdoor grill, do you have hot spots and cold spots on your grill? Anybody?
Sure.
Yeah, you have, it's not, no grill is uniform. That's not possible. In other words, you have different heat sources. Every point on your grill has a different heat source. So imagine your table in front of you was a grill top. Every point has a different heat source. So you can tell where the hotter spots and the colder spots are, and you can do certain things. So what the insurance company does is they go into this big building where the huge fire occurred. They can actually, using what are called heat signatures, basically dissipation rates of using differential equations, a little more complicated, but the same type of stuff. They can pinpoint the exact location in 3 dimensions, exactly where the fire emanated from. It's actually not as complicated as you think. And so when they find it and they get to that outlet and they see all the fried wires and things like that, they go, that was an accident. When they find that one spot and they find the down to almost molecular remnants of the gas-soaked rag, which they can absolutely 100% of the time always locate, it's arson. A crime has just occurred. And it's usually a really big one because it's a multi-million-dollar building. They use Nunes Law of Cooling, kind of a 3-dimensional version, to pinpoint the location where the fire started. To me, it's like unbelievably cool. It's really complicated mathematics, but once you have it, the person going out there figuring it out isn't, doing an equation. They're just using a simple computer program and other things. But the fact is that you can actually make your conclusions this way. So Nunes' law of cooling is basically just a really simple way of fairly accurately predicting the future or calculating something in the past if it's of a short time interval. Again, the closer you get to the ambient temperature, then the less change there's going to be in your temperature given a fixed period of time. Does everybody understand that? If in 10 hours the temperature is only changed a fraction of a degree, hard to work with because now the precision of my instruments comes into question. Just how good is my measuring? But for short durations of time, like the cup of coffee for a few minutes, extremely accurate. So this is the first of the differential equations that we've dealt with, the population growth form. Tomorrow, we're going to do a slightly higher version using some of the same math we did today, but we're going to extend it a bit further. So that's where I wanted to get to today. Like I said, some of the coolest applications. I love Newton's Law of Cooling, by the way.